recording. And good. Go ahead and get started. Okay. Hello. My name is Christiaan Masucci. Welcome to my presentation. Today, I will be presenting on GPU efficient graphic neural network training by optimizing graph data I/O and preprocessing. When I was looking for a paper, I was happy to find a topic related to neural networks as they go along with my topics in artificial intelligence, which I'm currently taking as a course. This research was brought upon by many researchers at ByteDance and many other institutions and universities who offered assistance because they need to improve their graphical AI functionality. Without further ado, let's get into it. In this paper, the researcher's main topic is graphic neural networks, or GNNs, as referenced throughout the presentation. Graphic neural networks are learning networks that can read graphs and make inferences about them. These inferences include node prediction, edge prediction, and node classification. Here on the bottom, I show what a very basic graph could look like with its edges and nodes, as you can see here. This is very small, obviously. The researchers chose this topic because the current graphic neural networks still have many problems that need to be resolved. These problems reside in their inability to handle and train large graphs that can scale up to millions, even billions of nodes and edges. A lot of the problem is focused on the pre-processing stage, where there are a lot of bottlenecks occurring. Allow me to give an overview of the article and its contents. The researchers' main goal was to discuss BGL, which is the name of their new graphic neural network training system. The authors wanted to compare their new system to the current graphic neural network to prove that it outperforms in every standard. The researchers were hoping to find and achieve a graphic neural network that could speed up operating times for the system and make GPUs more efficient overall. The author's main improvements included building a dynamic cache engine in order to minimize their feature retrieval traffic. Second, they looked to reduce cross-partitioning communication by improving the partitioning algorithm built off of previous algorithms. And third, the researchers looked to achieve resources isolation to reduce contention of crucial data. When we look at the challenges that the authors had to overcome in this paper, there are three main topics that were more challenging than others. First is the ineffective caching for node feature retrieving. When a large graph is being processed, the volume of data overloads the workers. Workers are part of the worker machines within each GPU. The workers are the ones who run these batches through the graphic neural network model and calculate the loss function. The next challenge is graph partitioning algorithms and their inability to handle giant graphs. This happens because of the high memory complexity it takes to handle these graphs. The researchers need to develop an algorithm that is, one, not too complex for the GPUs, and two, can handle large graphs with billions of nodes and edges. The third challenge that the researchers came across was the data pre-processing stages, contended for resources. And pre-processing stages become much more complex in graphic neural networks than in deep neural networks. Giving more resources did not seem to be the answer, though, because when provided with more resources, some stages acquire more resource than needed, causing blockages and backups. Here, I will cover some of the key terms mentioned that play an important role in the research. First, we start with cross-partitioning, which is important because it is where one of the key bottlenecks resides in graphic neural networks. Cross-partitioning essentially means that the same function would have to be run over every server individually instead of in a group. you can understand how this would cause major overhead and slowed performance. So the researchers improved their own partitioning algorithms. Partitioning algorithms affect the sampling overheads in two ways. First, they determine the cross-partitioning communication overhead. And second, they determine the load balance across graph store servers and sample processes. Next, we look at graphic neural networks. As stated at the beginning of the presentation, graphic neural networks are machine learning algorithms that can read and interpret graphs. They can make inferences about the graphs, such as node and edge prediction. Graphic neural networks stem from deep neural networks. Deep neural networks are a class of machine learning algorithm that aims to mimic the information in the brain and learn like the brain. The next term that is important is caching. The definition of caching is to store files in a temporary location for future use. This is extremely helpful when trying to save space on a GPU or when trying to access files quickly. In this article, the researchers create their own cache engine that is used for feature retrieving. This engine uses a system algorithm co-designed to minimize overhead, which is important because it utilizes every piece of the system. Now, let's look at some of the current problems that are happening in graphic neural networks before we look at the solutions that are provided in the article. First, we look at the feature retrieving traffic. The current approaches to feature retrieving is a static design that handles all of the caching in the pre-processing stage. Static caching has a low hit ratio when the graphs are too large and only a small portion of nodes can be cached. Next, we look at cross-partitioning communication using partitioning algorithms. Existing cross-partitioning algorithms either do not accommodate for large graphs or they ignore multi-hop neighbor connectivity inside of each partition. This leads to heavy cross-partitioning communication because in graphic neural networks, the sampling algorithm usually requests multi-hop neighbors from a given node. The final problem discussed is the data contention in pre-processing. Pre-processing of graphic neural networks is very complex compared to its deep neural network predecessor. This amount of complexity leads to resources fighting for CPU and bandwidth resources. The current systems simply ignore this and let the pre-processing stages fight freely. Also, some stages do not scale well even when given more resources. They could acquire more resources than needed, leading to backups in the pre-processing stage. Next, we will discuss the researcher's solution to these problems and the design implementations to solve them in their new BGL system. First, we look at the feature cache engine that will provide a solution to low hit ratio from static caching. The feature cache engine uses dynamic caching, which means it will constantly update the cache during runtime rather than only during pre-processing. The decision on which policy to use was difficult as most policies have a large overhead. To solve this, they used proximity-aware ordering, which visits nearby nodes to the mini-batches, in a combination with first-in, first-out ordering, or FIFO, as most people know, to create the optimal caching policy. The next inclusion to the feature cache engine is it maximizes the cache size. It does this by implementing a multi-GPU cache which jointly uses memory from GPUs and CPUs to create a two-level cache system. Each GPU has one cache map and one cache buffer. The researchers ensure that there are no duplicate entries among cache buffers to ensure that there is no wasted memory. The second solution mentioned in the article was the improvement of graph partitioning algorithm. Their goal for this new algorithm was that it could scale to billion-node graphs, utilize multi-hop connectivity, and train the load balance. Their new algorithm consists of two processes. These types are block generator and block assigner. Block generators do as they sound, which is create blocks that act as nodes connected to smaller version of the same graph. Block assigners collect blocks in these smaller graphs and then assign them to their own partition. The final solution mentioned by the authors is the improvement of resource isolation. They achieve this by focusing on resource utilization and training speed. The researchers divided the trainings into 8 pipelines that span across the CPU, GPU, network, and PCIe. The researchers then used a profiling-based resource allocation to assign the isolated networks to different pipeline stages. Doing so minimized the completion time of all stages of the pipeline, essentially making it as optimal as possible. Now, let's look at the implementation techniques the researchers used for their new BGL system. First, the authors used over 7,000 lines of code while making the system. They use over 4,400 lines of C++ code and over 3,300 lines of Python code. The researchers reused some of the deep graph library implementations, such as Graph Store module and GPU backend. The authors also used the graph processing module from Gminer to assist in the partitioning. The researchers found that NVLinks are a requirement for their system. When tested without them, they found that throughput was decreased by up to 50%. With so many GPU operations occurring, the researchers needed to make a cache processing asynchronous. They did this by queuing all cache GPU operations into a dedicated CUDA stream, which stands for Cache Unified Virtual Addressing. This implementation allowed for fast GPU peer-to-peer communication on each cache process. The authors took care in making sure that there is no interruption when looking at inter-process communication. The researchers use separate processes for the sampling, feature retrieving, and graphic neural network computation stages. The researchers also used shared memory to avoid copy of memory over different processes. Next, we move on to the evaluations that were taken by the researchers to ensure the productivity of their BGL system. First, we will look at the methods taken during evaluation and the resources used during evaluation. The researchers used a testbed of 4 GPU servers and 32 CPU servers. Each GPU server has 8 Tesla GPUs and 356 gigabytes of memory. Each of the CPU servers has 96 CPU cores, and 480 gigabytes of memory. All servers are connected using 100 gigabytes per second Mellanox NIC. For their datasets, the authors used 3 datasets. 2 public graph datasets, OGBN products and OGBN papers, and 1 web graph dataset called user item. As seen on the right here, there are different sizes to each data set. This includes different size nodes, edges, feature dimensions, classes, training sets, validation sets, and test sets. The researchers evaluate BGL using 3 representative graph neural networks: GCN, or Graph Convolutional Network, GAT, or Graph Attention Network, and GraphSage. When picking graphic neural network frameworks for baselines, the authors chose 4 of the most widely used. The authors chose Euler, which is a distributed graph learning system built in TensorFlow, DGL, DGL is a deep learning library for graphs and is compatible with multiple frameworks. PyG is an extension of PyTorch, which is a deep learning network specifically made for graphs. Finally, PA-Graph is a sampling-based graphic neural network that supports the static caching on GPU. When taking these measurements, DGL uses METIS for small graphs like OGBN products and random partitioning for large graphs. Euler, on the other hand, uses random partitioning for all of its graphs. Comparatively, the algorithms presented by the researchers in BGL are just two-hop neighbor algorithms. Now, let's look at the findings that came from the evaluation presented in the article. We look at the overall performance of the BGL system over many different measurements when we look at the overall performance, there are 4 key factors that make a major improvement for the system. These factors were all measured using sample per second, which is the key metric throughout the evaluation. When looking at the different frameworks, BGL achieved up to 69 times faster speeds than Euler, which is the largest difference. BGL achieved 30 times faster than DGL, 3 times faster than PyG, and 3 times faster than PyGraph. When comparing different graphic neural network models, BGL achieved higher performance than any of them. It was up to 30 times faster than GraphSage and GCN models. When up against GAT and BGL, still has performance up to 8 times faster. When we look at scalability, BGL also outperforms every other framework. DGL was shown to only have 3 times speedup when CPUs increased up from 1 to 8. With BGL's implementation of the NVLink, they are able to increase bandwidth and reduce their feature retrieving times. The last factor is GPU utilization. BGL was able to achieve 99% GPU utilization, both using a single GPU and when scaling to multiple GPUs. This is a major improvement when you compare that to DGL's 38% utilization and GraphSage's 10% utilization. Below, you can see changes in throughput over the different models. When we look back at the changes that the researchers made, we can see that they achieved all of their initial goals. There are 3 main changes that the authors made. First, we look at their feature cache engine. The purpose of the feature cache engine was to improve feature retrieving time in the network. We can see in figure 13 here that the feature retrieving time was significantly lower than all other systems, even with the increase of GPUs. The feature retrieving time was reduced by 98%, 88%, and 57% when compared to Euler, DGL, and PA-Graph, which is a major difference. The next impact made was from the graph partitioning algorithm implemented by the researchers. The main comparison was between BGL and G minor partitioning. As seen in figure 14 here, BGL was able to drop the sampling time by 14% on OGBN products and 10% on OGBN papers. This reduction in sampling time originates from the reduced cross-partitioning that BGL implements. The final improvement made by the authors was their resource isolation mechanism. As you can see in figure 17 here on the bottom right, the BGL is able to achieve the highest throughput when compared to Euler, DGL, and PA-Graph. BGL is able to achieve throughput that is 2.7 times faster than any other system. I would like to look back at some of the research-related works that the authors mentioned that assisted them in their journey. Sorry. We first look at partitioning algorithms. When dealing with large graphs, it has been the case that random, round-robin, and linear deterministic greedy are the most used. They have typically provided the lowest overhead, but that's not the case in VGL. Other frameworks that have not been included are AliGraph, which is made up of distributed graph storage and optimized sampling operators. AGL is also a relevant graphic neural network that is scalable with good system properties, but does not use GPU acceleration like BGL does. Next, let's look at the future of graphic neural networks. Still has strong potential. While the researchers may have made improvements allowing graphic neural networks to scale to billions of nodes, that may not last long. With data constantly expanding and more servers filling up, graphic neural networks will soon need to be able to scale to trillions of nodes, if not quadrillions even. We have seen as deep neural networks have evolved and eventually brought us graphic neural networks. This shows how the future is endless in this field and more improvements can always be made. While BGL shows massive improvements over the best graphic neural networks today, new technologies must emerge that show even more improvements over BGL. For the final conclusion that could be understood from the article, it was that BGL is currently one of the best performing graphic neural networks of its time. As shown in the evaluation, BGL statistically outperforms every other graphic neural network framework that is currently in use. In total performance, BGL is able to achieve almost double the speed that the best system can achieve. The authors were able to achieve their goal of making a graphic neural network that can scale up to billions of nodes with optimal speeds. And that is all. I want to say thank you for listening to my presentation.